Hi everyone, my name is Thilo Krachenfels and I will present our work entitled Real-World Snapshots versus Theory, Questioning the T-Probing Security Model by Fatmir Ganji, Amir Moradi, Shahin Tajik, Jean-Pierre Seifert and myself. Our work shows that assumptions used for theoretically developing countermeasures against side-channel attacks do not always reflect the real world. This talk will be structured as follows. After a short overview, I will present the necessary background knowledge, and afterward I will talk about our approach, the experimental setup, and the results of our experiments. Masking countermeasures have been developed to provide side-channel analysis security for cryptographic algorithms, and they have been used or are employed in, for instance, banking cards for more than a decade. The security is mathematically proven in the T-probing security model, which I will explain in a bit more detail on the next slide. Its central assumption is that the number of available and independent probes is limited. This is also a realistic assumption when considering traditional side-channel attacks such as microprobing, power analysis, or EM analysis. For instance, here you can see a prober setup with at most 8 probes or 3 electromagnetic probes. In our work, we show that this assumption of having a limited number of probes is not realistic when considering optical side-channel analysis techniques such as laser logic state imaging. But before going into more detail about this, let me give you some details on the T-probing security model. Masking countermeasures are built on the two principles secret sharing and multi-party computation, and Boolean masking is the most common scheme to split the inputs of the algorithm into multiple shares. And typically all but one share are random numbers, and then the final share is the XOR result of all other shares and the actual secret. And then the intermediate computation of the algorithm deals only with the secrets split into the shares, so computation will never involve the entire secret, which means, all shares. And in this way it can be assured that the adversary cannot learn any sensitive information from T physical probes when the implementation uses T+1 shares. This is also because of the randomization which is used for the secret sharing. And mainly due to this randomization, no measurement repetition is possible. However, one should not forget that there's also another kind of requirement in masking schemes, and that is that the secret shares and intermediate results must be stored in registers on the chip. And this is where our attack technique comes into play. As I've mentioned before, the technique which we are using is laser logic state imaging, which is an optical probing technique, and it's conducted through a microscope-based setup where the chip backside is scanned with a laser. And since the bulk silicon is transparent to light with wavelengths above 1.1 micrometer, the light can enter the silicon and is reflected also back from the chip. And while the light's in the chip, it is modulated by different carrier concentrations in the chip. The reflected light is then sensed by a detector, and for LLSI, for instance, it's then fed also through a bandpass filter. This leads me already to EOFM, on which LLSI is based. EOFM stands for electro-optical frequency mapping. And on this schematic on the right hand side you can see that some transistors are switching with a periodic frequency, in this case 1 MHz. When scanning with the laser, the light is modulated by those transistors switching at 1 MHz, and therefore the signal can pass a bandpass filter set to that frequency, which results in bright spots on the LLSI response image. You can also see here that transistors which do not change their state periodically cannot be detected by this technique. However, this is different with LLSI. The trick is to modulate the supply voltage of the transistors, and therefore transistors which are switched on will be visible on the LLSI response image, and transistors which are switched off not. So basically on and off states of transistors can be distinguished due to carrier density differences which influence the light reflection. Now let's look at a CMOS memory cell. It is which is used, for instance, in FPGA registers and flip-flops. These kind of memory cells consist mainly of two cross-coupled inverters, where two transistors are switched on and two transistors are switched off depending on the bit state this memory cell holds. And therefore, when scanning using LLSI, in this case the top right and bottom left transistors are switched on, these will show up as bright spots on the LLSI image. Therefore we can extract the bit state. You can imagine that if the opposite bit state is stored in the cell, top left and bottom right transistors will be switched on and the response image would be simply flipped. So to sum up, LLSI is capable of capturing snapshots of on-chip memories. For our attack approach, we are considering two scenarios. One scenario where the memory locations of the key registers are known, and one scenario where they are unknown. In the first scenario, which is more simple, we only capture snapshots of the key registers and then extract the individual shares from the images, so the bit values from the images, and can obtain the key by simply XORing the shares. In the second scenario, we don't know in which registers of the design the key shares reside, and therefore we capture snapshots from all registers of the design from different clock cycles, extract the bit values, and then use a SAT solver to find the key register locations and therefore also the key. As implementation under test, we used the AES DOM implementation, which is freely available on the internet and can be built with an arbitrary protection order. For each share of the key, there are 128-bit key registers and also state registers for the plaintext and then ciphertext. Plus, there are some extra registers for intermediate results and the key schedule and SBox implementation. But we are mainly targeting the key registers. Upon start of the encryption operation, the plaintext and the key are shifted into state and key registers byte by byte. And this is how it looks like. So if you have the state registers in the top row and key registers in the second row, you can see that after the 16th clock cycle, exactly here, all key shares will be loaded into the key registers, and this is what we target with our LLSI extraction. As device under test, we used an Intel Cyclone 4 FPGA, which was manufactured in a 60 nanometer technology. Here in the center you can see a reflected light image of the entire chip, and on the right hand side a closer look into the configurable logic blocks. So as first step, we somehow analyzed the target FPGA and tried to extract the content from a single memory cell or flip-flop. Since it's an FPGA, we could easily run another program or switch the register's content at our will. Here you can see the LLSI signal overlaid on an optical image, and for bit value 1 you can see large spots on top left and bottom right of the image, whereas for bit value 0 there is a big spot only on the top right corner of the cell. When subtracting the two LLSI responses, it gets even more clearly that there only stays a signal inside the cell boundaries, which we have highlighted in yellow here. So this previous slide has already shown that subtracting two LLSI images can really help to read out the content of the registers. This is an image showing the first byte of 3 key shares. And from the actual LLSI image, we have subtracted an LLSI image on which all registers store the bit value 0. You can see that the key can easily be extracted. All cells showing a big difference contain bit value 1, and all cells which are only kind of grayish contain bit value 0. And of course, the extraction can also be done in an automated fashion. And for this, we used classical image recognition techniques by first cutting out each individual cell. And we had to take into account that every second cell is flipped, so we had to flip it back. Then we chose 2 template images, one for bit value 1 and one for bit value 0. And then we simply calculated the cross correlation between each cell and the templates. And this table clearly shows that the correct bit value can be extracted using this approach. And it works pretty reliably. We could extract all 128-bit key shares from a 3-share and even from a 5-share implementation without any bit errors. So that was pretty impressive to us. But now there's still the case where the key registers are unknown and simply extracting the memory content doesn't help to reveal the secret key. And as I said, for that we used SAT solvers to find the set of key registers within all registers of the implementation. We first simulated different masking orders and clock cycles available to the solver, and in general you can see that it becomes easier for the solver to reveal the key registers when snapshots of more registers are available. And also for higher masking orders, the minimum number of clock cycles available as snapshots for the solver increases. If you're interested in learning more details about the SAT solving part, please take a look at our paper. To prove that this approach works, we first extracted all registers from a 2-share implementation using our automated cross-correlation based approach. The design for this 2-share implementation contains over 720 registers. And as you can imagine, that takes some time, and it took 24 hours to create all those snapshots from the 12 different clock cycles. However, the key extraction using the SAT solver then only took 1 hour and 47 minutes. And I should also mention that the extraction time, so the time for capturing and solving the SAT solver, increases basically linearly with the number of registers contained in the design. To encourage others playing with our data and trying to improve the key extraction, we made all snapshots and the extracted bit values of our experiments available online. The link can also be found in our paper. This already leads me to the conclusion. We have started with the observation that the probing security models assume a limited number of probes available to the attacker. While this might hold true for classical side-channel attacks such as power or EM analysis, with optical side-channel attacks we virtually have an unlimited number of probes available. We've shown that we can extract the full AES keys of masked implementations of AES with different numbers of shares. Therefore, our main takeaway of this work is that cryptography should not rely on the complexity of physical attacks. These are the references I used for this presentation. Thank you very much for your attention.